Okay, so welcome. This is the AQA AS Physics video. This is the Unit 2 past paper, June 2009. Okay, what we've been given here is I've tried to draw this diagram, and it's essentially students investigated how the extension of the rubber cord varied with the force needed to extend it. So basically she's just extended a rubber cord and this is plotted the results. Now I'll try to show you on here the difference between the two curves. Okay, so the red is obviously mentioned as the loading curve, and the blue, which goes back to the same point, is known as the unloading curve. Now on the graph, okay, they put increasing force and decreasing force. Now I think that's purely there just to confuse you. Obviously, depending on how you've learned the topic, personally I learned it as loading and unloading, but you just think, well, loading is applying a force and unloading is removing that force, so in other words, increasing and decreasing force. So that's why they put that in there, but personally I think that's a little bit, you know, with your mind might not be thinking that in the exam. We just got to think, well, we've not done anything else that is like this. Okay, so 4A part 1, give a reason why the graph does not, graph shows the rubber cord does not obey Hooke's law. Well, just to recap, Hooke's law says that the force is directly proportional to the extension. Okay, so F equals K times delta L, where the constant proportionality is the spring constant. In other words, what it's saying is the force of, the graph of force against extension will have a constant gradient, because if we've got force here and extension here, when we work out the gradient, which is force over extension, or force over delta L, we should get K, which is a constant, okay? And that quite clearly does not have a constant gradient, okay? So that's what you'd say for this. You'd say, Hooke's law implies force is proportional to extension, directly proportional to extension, hence constant gradient, which is not shown by constant gradient, which is not shown by the graph above. Okay, and that's all you need to that's all you need to show really, because there's only worth 1 mark. Even though they put quite a lot of writing space for 1 mark, you do need to state both of them points to get the 1 mark. So, and obviously they don't split it onto half marks, you don't get that. So really it's just saying what Hooke's law implies on a force against extension graph, and then the other words, well, it's not really a new point, I guess. It's just emphasising the fact that this graph does not show that, but you need to state both halves of the explanation even. Okay, so 4A part 2. 4A part 2 says, give a reason why the graph does not shows the rubber cord does not exhibit plastic behaviour. Plastic behaviour, this is a test really. Do you know what is meant by all the terms of the graph? Plastic behaviour is another word, another way of saying plastic deformation. Okay, because obviously plastics exhibit plastic deformation, the key words being the plastic in there. And plastic deformation, just to recap, is where the string or whatever you're stretching extends to a point where it is permanently extended. In other words, if you were to get a graph, now I do apologise for the crappiness of this graph, but if you were to do something that did exhibit plastic deformation, basically you would have a plastic deformation point, and when you return that extension, that's not a very good example actually, when you return that you would get basically a permanent extension. So even if you took all the load off, the unloading curve would not reach the same point that the loading curve started from. In other words, you would have a permanent extension. And this question is saying, give a reason why the graph does, shows that the rubber cord does not exhibit plastic deformation. So you don't need to explain what plastic deformation is. That isn't what this question is about. That was just purely to remind you of what it is. So the answer, what you would put for this, is just saying, well, the unloading curve, or I don't know which way you want to word it. Essentially, when the force has been removed, there is no permanent extension. Okay, so you just put there is no permanent extension when all the force is removed. Okay, so there is no permanent extension. It's as simple as that. It's really just a case of word association, remembering. It's just a knowledge test. That really is no there's no calculation obviously required in that. This next point, again, a bit of a knowledge thing. What physical quantity is represented by area shaded between the loading curve and the extension axis? Now I'll try to build this up. If it doesn't come straight away, then it does need a bit of building up, obviously. So what we've got here is we've got force and delta L. Now delta L is an extension from its unstretched length. In other words, it is a measurement of distance. And when we do force times distance, okay, I know that says delta L, but it's the same as the distance. The extension is a distance measured in centimetres, okay, so it's a measure which you measure distance of it, you know, an object has travelled X amount of metres in a certain time, okay, same kind of thing in terms of, but I'm just, instead of putting delta L, to associate it with an equation you already know, I'm just going to put D instead, okay, and force times distance, we should know, the equation for that is work done. In other words, work done, okay, is an answer you could put to this question. It's the work done extending the string to a certain point. Now it's not asking for the area between the loading and unloading curve. All it is asking for is, if we just, you could almost ignore this unloading curve for the moment. If we wanted to extend it up to, you know, if we applied 40 newtons or whatever, and it wants to know what that area there represents, not the area between the curves, just the area below a point on the graph. And that is quite clearly the work done to extend it to that point, or in other words, the energy put in to extend it. Same kind of thing, okay? But I'm talking about the work done, and hopefully you get why that is. Now the next question says, describe with the aid of a diagram, okay? So it's all about coming up with your own experiment for this. Okay, so it says, describe with the aid of a diagram the procedure and the measurements you would make to carry out this investigation. Oh, sorry, I might have missed out a little bit of a... Is it? No, I haven't. Sorry. The procedure and measurements you would take to carry out this investigation. So basically, it's just asking about... Sorry. Yeah, just asking about, you know, if you were going to come up... Yeah, so it's asking about this experiment in general. How would you... Because it's not told us how the student has set it up, okay? We need to explain how they would have set it up and how they would have got the results they did, okay? Because normally when they do this, they will tell you a little bit about the experiment, but they haven't. So obviously the wording for that part of the question, I think, is a little bit annoying, to be honest. But really, obviously you need to draw a diagram for this. Now, it doesn't have to be a brilliant diagram. It just has to show the basics, really. You have to have a labelled diagram, okay? I don't think he mentioned it, but you know, you should do when you're doing something like this, okay? So what you might have, and instead it is totally up to you how you design this experiment, but the main principles apply. Obviously you have, because it's all Hooke's law experiments and carry the same kind of principle. So if you get any question which asks you to design you know, an experiment to test Hooke's law or some variation on Hooke's law, what you have to do is you have to set up an experiment where you want to have an unstretched length and applying a force, a known force to that, and then working out the extension. Because obviously the two things you need for Hooke's law, it generally force and extension, or they might give you, you know, obviously they might give you the spring constant, ask you to work out the force of the extension. But when you're coming up with a, you know, a graph, okay, like the one here, it's the force and the extension that they want you to work out. Okay, so what I've got here is some kind of table. Okay, yours doesn't have to be, it doesn't have to have such artistic merit as mine does. But what we've got here is we might have some kind of clamp stand. Okay, and so my drawing is very crap. This here, well, I put arrows on, that's meant to represent the rubber cord, okay? So, I mean, because, you know, your artistic skills might not be as good as mine, what you need to do in the exam is label absolutely everything. Obviously, you know, hopefully you can tell it's a table, but the key scientific bits as well. So, you know, your clamp stand, okay? And then I might just draw a weight on here, so you're obviously going to attach some weights. Now I'll come into why that is in a minute. Okay, so weights, and you might be putting your own weights, okay, but you probably will explain that in your explanation. Okay, so I would show that one weight is attached, just to show how you would attach it, and then as I said, it doesn't really matter, but it just helps the examiners to visualise where you would put them. Okay, and then just a series of other weights, and I would put them slowly increasing. You might want to label them in terms of 10 kilograms, 15. But they're not really interested in that. It's the fact that you're applying more weights, okay, and they're all known, okay. Because obviously if they're unknown, then that's stupid, really. Because obviously we don't know the spring constant, and if we don't know the force either, all we know is the extension, and quite clearly we can't plot a graph of that. Okay, so you don't need to. It's not ISA in terms of it's not GCSE where you have to say set up the equipment as shown above. Your A-level people, it's expected that you would not just draw something and go, well, yeah, I've drawn all this, but you're not going to set it up like that. I'm just going to confuse you. There's no point wasting paper, okay? Even though I probably kill about a whole Amazon rainforest every exam I write. Anyway, so the first thing you would say is, well, obviously you need to measure the original unstretched length. So measure the unstretched length of the cord. Okay, so that's the first thing that you would say of the rubber cord. Okay, and then what you would say is, obviously you would add the known weights and measure the extension. Okay, so you would add known weights, obviously increasing the weights by the same amount each time you want to add as well. So add each weight, obviously of the same amount each time, so you don't have to have that, but it will just give you quite a nice graph, okay, of the same each time, and measure the extension produced. Okay. And then obviously your next point would be about plotting that on a graph, okay? Now you would plot your results on a graph. And then you might want to just go on in your next few bullet points. You might have already mentioned it was always nice to cover all bases. You could talk about, what you would expect to see, okay? What you would expect to see. But because the question just talks about the fact that this rubber cord does not follow Hooke's law, we know the results of it. If we didn't know the results of this, then we would assume it does follow Hooke's law, but because they've told us the results that are obtained from this experiment, you would go on then, obviously, to talk about the fact that, so what you would expect to see for this, but what we'd know, okay, what we know happens, okay, and then you talk about, in that bit where you talk about what we know happens, you talk, as shown in the previous part of the question, this does not follow Hooke's law, so we would expect that, the force, even if we added the same force, we would get different extensions each time. I don't think we have to add that from that, but it's always nice, just as I said, just to cover all bases, especially if you've got a bit of extra time in the exam. But really, the key things, as I said, you might have drawn this slightly differently, okay? In other words, you might have set up the experiment slightly differently, but the key principles apply that you need to, for any experiment in Hooke's law, you need to have some kind of stand or something, well not some kind of stand, you need to have a rubber cord at an unstretched length, okay? And you need to have being able to apply some force and then measuring that extension. Oh, actually, wait one sec, there's something I've missed. Obviously, you need something to measure the extension with, and you probably need to explain that in where you measure the extension produced. Now, I didn't write it on here because I wasn't thinking straight, but you need to have some kind of meter rule or something, because obviously you just putting a little rule up, so it's not going to be as accurate. And that accuracy bit leads me on to a next point you might want to make in this part of the question. So you might want to talk about the fact that, if you didn't use weight like this, obviously you could calculate the weight you will be given it masses. You can calculate the weights, which is obviously a force, and that's what's the force which is applied. But you might have said, well, I'll just simply pull the rubber string down. Well, that's very good, and it will apply a force, but it's very hard to calculate what exact force without a Newton meter. So if you were to push it down, you would need to obviously encounter that into a Newton meter as well. Okay, so but I've applied weights because it's a lot easier to measure the actual force that they apply. Now, obviously, the masses you might want to talk about errors as well. Your next point, you might want to mention about errors. But as I said, the key thing is really about measuring the unstretched length, applying the force, and noting down the force and the extension, and then putting the results on the graph. And obviously, the other marks come from setting up, as shown. So key things like how you would measure it, measuring the unstretched length and labelling all the points on your diagram. Okay, and then the other few marks just simply come from spelling correctly. Now, the thing, as I said, that makes people think we have to write an essay on these kind of things is the fact that it says, using spelling grammar will be marked appropriately or whatever it is, and that just simply means, is your spelling right? Okay, so don't feel you have to follow, a whole other exam for that. Okay. Sorry, I do apologise. I've got the exam open on a tab on my computer, and it just decided to shut itself down. So I do apologise. Just make sure there's no other parts. No, there's no other part. No. Yeah, there's no other parts to this question. So thanks for watching. Hopefully, question 4. As I said, it's not too difficult. You still get it's quite a nasty paper because we've had 2 questions where we've had to do a bit of explanation, and generally you get 1 question where you have to do this kind of thing in terms of you talk about something. Maybe question 3B wasn't such a difficult one, but the fact that they almost made you write it as an essay is what I'm saying. It's a good idea to do bullet points, because if you were to write them 2 as essays, you would have wasted time in the latter part of the paper where it's just easy to get marks from calculations. Okay, so thanks for watching. Hopefully it's been you've been able to follow it, and we'll see you in the next question.